Good afternoon. My name is Akan C. I'm a researcher in Dudak Space Technologies Research Institute from Turkey. And I would like to present antenna subsystem of GAMALINK platform. Here we see the content of my presentation. First of all, I would like to give a brief info about GAMALINK platform. Then we will see functions of GAMALINK antennas, design requirements, design methods, studies in the general literature, conducted works, and finally we will see the achieved results through the project. GAMALINK is the acronym for generic SDR-based multifunctional space link. It's a hardware communication platform based on SDR, especially adapted for using in CubeSats. And this project has been founded by AP7 framework. And the consortium consists of Tekrar Space. This is the leader or coordinator partner of our project. It's from Portugal, and EVLX from Turkey, TTI Norte from Spain, University of Porto again from Portugal, Fraunhofer IS from Germany, and finally Dudak from Turkey again. On the top of this radio platform, several features will be implemented, and these are mobile ad hoc networking, Inter-Satellite-Link, named as ISL, attitude determination of one station relative to another, and GPS waveform reading and signal decoding, and also ranging between the satellites of constellation, based only on the transmission of communication signals. The entire design has been made taking into account the CubeSat constraints and the space environment. There exist different designs leading to develop modules relating to use of RF electronics, antenna, acquisition, and signal processing. And also, in order to save transmission power, we will also use beamforming capability by combining electronics and antenna modules for the communication subsystem. And as we know, antennas are basic final or initial elements for communication transmitter or receiver systems. And in GAMALINK, their main responsibilities are transmitting, receiving signals for ISL or ground communication, and GPS signal reception as well. So we can separate antennas in two types, S-band antennas and GPS antenna system. And for one CubeSat, we can see the S-band antennas in L-shaped form for beamforming, and also GPS antenna in yellow one for only lateral faces. And S-band antennas shall work for establishing a ground link or to perform inter-satellite communications as dual-way receive and transmit, and also attitude determination. They shall work in ISM band with enough bandwidth and appropriate polarization. We will see the values in the preceding slides. And GPS antennas shall be responsible for receiving GPS signals. These antennas are passive, since LNA part will be on GPS RF front end, and they shall operate at GPS civilian frequency band L1. In the first figure, we see the simple S-band transmitter architecture. There are three paths connected to S-band antennas. And also we see the phase shifters in order to obtain the beamforming on the platform. And here in this table we see the design requirements for the antennas. Operating center frequencies at ISM band for S-band, and GPS antennas for L1 frequency, as mentioned before. And our bandwidth is 15 MHz for S-band and 20 MHz for GPS. Our maximum dimensions are 30 cross 30 millimeters square for all of the antennas. And there will be 18 S-band antennas and 4 GPS antennas. All of the antennas passive. Our polarization will be circular. Input impedance 50 ohms, and our operating temperature is between -40 and 80 centigrade degrees, and surviving temperature is between -80 and 100 centigrade degrees. As is well known, there are 5 general antenna miniaturization techniques. One of them is geometrical shaping, including slope loading, bending and folding, meandering, and etc. And the other one is material loading, using with high dielectric or magnetic materials, lumped element or distributive element loading techniques. Optimization methods can be used also, like generic algorithm, particle swarm optimization, and etc. And finally, we can use electromagnetics metamaterials. But there are some physical limitations on antenna miniaturization, because when we miniaturize an antenna, it will affect its radiation characteristic like gain, efficiency, or polarization purity, bandwidth, and input impedance as well. The general theoretical limit is expressed in this relation, expressed in equation 1. Here, E is our bandwidth, eta is the antenna efficiency, K is the wave number, A is the radius of a sphere enclosing the antenna, and N refers to linearly polarized or single mode antenna for equals 1, and for N equals 2 refers to dual mode or circularly polarized antenna. And also we can relate this expression with quality factor, and it is clear that bandwidth and efficiency of an antenna are inversely proportional. When more bandwidth needed, antenna efficiency decreases, or vice versa. Moreover, a trade-off is inevitable between dimension and bandwidth efficiency product for a miniaturized antenna for our operating frequency. Since CubeSats are small platforms, general antenna designs and materials are not appropriate to satisfy the dimension requirements, and there are many studies to overcome this problem. In our case, there will be 16 antennas for lateral faces, so placement of solar cells can be a serious problem. And in the literature, there are studies about optical transparent and mesh antenna structure to overcome this problem. One of them is realized by Simons and Lee in 1997. And in this structure, a thin sheet of clear polyester with silver HT8 optical transparent conductive coating has been used. But the conductivity of this coating is very low at low frequencies. Then the applications were realized at 19.5 GHz. And another optical transparent antenna study has been realized by Katsuneros et al. And this is the transparent ultrawide and disc monofoil antenna as shown on the left figure. And here we see also the results for return loss and gain. And another optical transparent antenna concept is meshed conductor antenna structure. There are also many studies about it. And it can be a cost-effective solution for applications where the antennas need to be optically transparent. And here we see again a circular meshed printed antenna. In the left figure, you can see the design of the mesh structure patch, and also you can see the feeding of the antenna. This design is realized on 2.6 GHz, but especially for transparent and mesh antenna structures, feeding could be a problem. It could be very hard to use soldering since the metallized area over the antenna surface could be very thin, generally about 10 microns, and it's very weak, and also it reduces the mechanical strength against vibration forces, which might be a complication for space qualification. And another candidate is using dual band antennas to combine GPS and S-band antenna. But there are very limited numbers of studies for compact dual band circularly polarized printed antennas in the general literature for the required bandwidth. The closer ones have been reviewed, and the obtained total surface of one of them is about 50 cross 50 millimeter squares, and the second one is about 75 cross 75 millimeter squares. In our project, for one phase of CubeSat, there will be 3 identical S-band patch antenna elements to realize the beamforming. So, according to studies available in the literature, the most similar case is presented by Zhu et al. And here we see the configuration of the proposed antenna. This is dual-band circularly polarized antenna based on complementary 2/3 resonator, and also you can see the results for 2 operating frequencies. Minimum dimension of the antenna is dominantly determined by high resonant frequency of it. So even we tune first resonance frequency of the antenna to GPS L1, our minimum dimension will be determined by second resonance. Is that 2.7 GHz? Then its dimension will be 44.2 millimeter cross 44.2 millimeters. And when we compare the results for dual band and discrete cases, the discrete case is the most beneficial, as we see from this table. And in this project, we have aimed to use simple structures by implementing geometrical shaping and material loading techniques. These are Kelly-to-back cross-slot antennas, miniaturized slot microstrip antennas, and also the final candidate, small microstrip patch antenna with parasitic shorting strips, and we decided to use it, and also we see the results, but since time constraint, I'm going on. And here, for the miniaturized S-band antenna for GAMALINK, you see the return loss, gain, and also radiation pattern characteristic of the antenna. And for GPS antenna, we have also tried many type of antennas. Here we see the using high dielectric permittivity materials and its results. But when we use high dielectric permittivity, its resonance, bandwidth of the antenna is very narrow. So we should have quit it.
We have 1 minute left.
Okay. And finally, here we see the tabulated results of S-band antenna and GPS antenna. We satisfied the bandwidth, circular polarization, gains according to link budget, and the most important thing is the maximum dimensions. As we see here, S-band antenna 24 cross 24 millimeter squares, and GPS antenna is 28 cross 28 millimeter squares, and they are all pin-fed single port antennas. Thank you very much.
Are there any questions? No questions? Thank you very much.